All right, class, so say we're studying section 5.2, properties of common and natural logarithmic functions. We're going to be evaluating common and natural logarithms. So let's do some reviewing. To understand logarithms, you really have to understand the properties of exponents. So for example, 2 to the negative first power is the same thing as expressing one half. And any number to a fractional exponent, we take the number that's underneath that radical, or underneath that fraction in the denominator, and that's our radical. This will help us as we go through and evaluate logarithms. The logarithm, or log, is another way of writing an exponential statement. And again, if you understand the properties of exponents, then you can understand the properties of logarithms, because they go hand in hand. So first, let's look here. This would be an exponential statement. You have a number that's your base, the power, and then your answer. Is typically how we express it. So for example, 2 to the 5th power equals 32. In this case, 2 would be our base, 5 is our power, and 32 would be our solution. Well, in a logarithm, it's a little bit different. You still have the log base, and you say it log base 2 of 32 equals 5. So whenever you're expressing a logarithm, you want to know the base raised to what power gives you 32. And so the solution to log base 2 of 32 would be 5. To convert between logarithms and exponents, I like to use what I refer to as the circle rule. Notice in our vocabulary, both the logarithm has a base and the exponent has a base. In the equivalent exponential statement, the base will be 5. So we start here at the little number, the base of the log. So we say 5, and then we go across the equal sign. 2 to the 3rd power equals 125, which is a true statement. So whenever you're evaluating a logarithm, you're really asking yourself the question, what power makes the statement true? Let's do another one. So the log base 2, so that means my exponent base is 2, to the 10th power has to equal 1024. To switch from exponents to logarithms, again, we always start with the base. Because 2 is the base of our exponent, 2 is going to be the base of our logarithm. So it's 2 to the 8th, or it's 2, log base 2 of 8 will equal 3. Again, you're always asking yourself what power makes this statement true. Let's do another one. So since our base is 4, it would be log base 4 of 1024 equals the power of 5. If we don't write a base for the logarithm, we typically mean that it's the log base of 10. It's known as the common logarithm because it's the one that's most often used. For basic evaluations of logarithms, you can use the log button on your calculator, but it's always going to be a base of 10. Some of the newer models of scientific calculators will let you put in a different base, but for the most part, if you try to use the log button on your calculator, it's going to give you a base of 10. So let's evaluate without a calculator. Again, for the first one, I didn't write a base, so that means that the base is 10. I always like to think of it as an exponential function. So 10 to what power is going to give me 10,000? Sorry, 100. 10,000. So I could rewrite 10,000 as 10 to the fourth power. So that means that 4 would be the solution to this logarithm, because 10 to the fourth power is 10,000. The log base, or the log of 10. You could also say the log base 10 of 10. So again, think of your circle rule. 10 to what power will give you 10? And we know that to just be 1. The log base 10 of the cubed root of 10. So again, set it equal to x. 10 to what power is going to give you the cubed root of 10? Well, I can express a cubed root as a fractional exponent. So that means that x has to equal 1/3. And the log base 10 of negative 7. 10 to what power is going to give me negative 7? Now let's think for a second. Is there any x that I could come up with that is going to make 10 be a negative number? If I plug in a negative number in my exponent, I get a fraction. If I plug in a fraction, I get some kind of radical. So there's no solution here for this situation. You cannot take the logarithm of a negative number. A natural log is a logarithm with a base of e. We call it the ln. There will probably be an ln button on your calculator. But ln and the log of e are essentially the same thing. And in case you forgot, e is another irrational number, kind of like pi. E about equals 2.71828. And it continues forever, just like pi does. Another important property to note, which we kind of already discovered back here, is that if the base of the log and the base of the exponent are the same, when you evaluate the logarithm, you're just left with the exponent. The same thing if you have an exponent raised to a logarithmic power. If the base of the log and the base of the exponent are the same, you're just left with x. You're just left with whatever number would be in that logarithm. So if they're the same, and you have a logarithm and an exponent, they'll cancel each other out. So the log base 10 of the square root of 43, the log base 10 and the 10 can cancel, and you're just left with the square root of 43. Remember, the ln of e to the 15th power, I don't need to evaluate e to the 15th power, because ln is the same thing as the log of e. The e's cancel each other out, and I'm just left with 15. Same thing here. E to the log base e of 6, I'm just left with 6. That's the only way I can make that statement be true. And then here's another one. E to the ln of x plus 1. The e and the natural log are going to cancel each other out, and you're just left with x plus 1. That's all I have for you today. Please write down any questions that you have, and I will answer them in